We're going to finish up chapter 7 today. And then tomorrow we're going to start chapter 8. We're doing a lab, but I'm going to lecture for a large percentage of the lab. Chapter 8 and tomorrow's lab go together. Any questions before we get started? No? All right, we're going to talk about functions of state or state functions. You know, what is a state function? A state function, we call this a state, you know, an energy state here. And we have some scale here. This scale here is for U. And what can you tell me about this? Where's the 0 point? You know, that's called an absolute zero. Where's the absolute zero of internal energy? It's not there. And so this is kind of arbitrary units here. But anyway, we have some energy state here, some energy state here. What is the energy state defined by? Energy state's defined by kinetic and potential energy. What is its temperature? What is it made out of? That's going to define the energy state. And so, you know, whether this is exothermic or endothermic, if it's endothermic, we go up in energy. Exothermic, we go down. Let's look at an exothermic. We'll start off with U initial here. U initial is going to equal, you know, there's going to be some temperature associated with that and some kind of potential energy. So U initial is equal to what? It's equal to EK initial plus PE initial. And so I need to keep moving here. So U final is equal to EK final plus PE final. And these are the states. So this is the initial energy state, this is the final energy state. And we have something called delta U. Delta U, which is a change in internal energy, this is just review, by the way, is equal to U final minus U initial, which is equal to delta EK plus delta PE. So basically we just take the final, actually delta EK is the EK final minus EK initial, delta PE is the PE final minus PE initial, so that's what we end up with. The state functions, these are, you know, always the same, they just depend on the state, you know, and so this is the state function. That means potential energy is also a state function and kinetic energy is also a state function because the changes in those only depend on the final. Like for example, if we look at delta kinetic energy, we just look at the delta T. You know, delta T is the change in temperature. Delta T just depends on your final temperature and your initial temperature. Does it depend on how you got there? So let's say I had a delta T of minus 100 degrees C. So we went from this temperature to this temperature. It doesn't matter how you get there. You could shoot up in temperature and then drop way back down, but you know, it just depends on the initial and the final. Well, that's the definition of a state function. State functions only depend on the initial and the final state. And that's it. And so the state functions depend only on initial and final state. What else is what else is delta U equal to? Q plus W. Q plus W. Well, it turns out that Q plus W are not state functions, even though this is all a state function here. Q plus W, these are what we call path dependent. And so here we see functions of state, and then we go over here, we see path dependent functions. Sure. And so what's the difference between a path dependent function and a state function? Well, a state function is always the same. You know, as long as you start from this state and end at this state. Path-dependent functions depend on how you get from one state to the other, the initial to the final. And so path-dependent functions can vary, whereas state functions do not vary. Path-dependent functions vary depending on how the change occurred. So we'll just say how the change took place. And so what that means is this, we're always going to get the same amount of energy. And that same amount of energy is going to be the sum total of Q plus W. But how big Q is and how big W is depends. So for example, if Q is bigger, then that means W has to be smaller. Or, if W grows bigger, then the heat is smaller. And so we could look at an analogy here with a slide. If we have like a playground slide here, and this person at the top here, this person at the top is going to have higher potential energy. We call this gravitational potential energy. So U initial here, this higher potential energy. Now let's say the kinetic energy, well, this is 25 degrees C, right? And so this is at 25 degrees C. And then in the final, U final is going to be down here. This will be U final. And so they just slide down here like this. This is going to be at lower potential energy, and so there's going to be a delta U here. And the delta U is going to equal Q plus W. Now what is the change? Well, in terms of U initial, we'll just say U initial is at 25 degrees C. U final should be at 25 degrees C. But what's going to happen in going from there? There's going to be a change in potential energy, and that means what goes to the surroundings? Heat and work, because delta U is equal to Q plus W. Now, did this person do any work sliding down? No. Basically, all that potential energy there was converted into heat, right? Because the slide is going to get warm, especially if it's a metal slide. You feel that. You can feel the heat radiating off of it, right? This is what we call friction. Okay, so Q. So in this case, no work is done, and all this is radiated off as heat. So all this excess potential energy change. Does that make sense? All right. And so here, this is a state function, so the amount of energy is always the same going from U initial to U final. So let's try another way of sliding down the slide. Another way is to lubricate the slide. So we'll put oil on the surface of the slide. If you put oil on the surface of the slide, then there should be very little friction, right? And so we'll just say we'll oil or lubricate the surface. Well, if you oil the surface, what's going to happen? Well, maybe some of that potential energy is going to be converted into kinetic energy, and they're going to shoot out, high translational energy. But instead, we're going to tie a rope around this person attached to a pulley here. And this pulley is going to have a weight down here. The weight is going to be approximately the same. Actually, let's just make it the same mass. If the weight is the same mass, then, actually they're going to get stuck here, but we'll just make it slightly less. And so now as the person slides down, delta U is a state function, so delta U is exactly the same as before, except in this case, are they going to generate much heat? Well, with a weight there, they're going to go down extremely slow, especially with the surface oiled like that. And instead, they're going to pull up this mass here, this weight. And so delta U here is Q is going to be, well, we'll just say close to 0, and all this is going to be converted into work. I'm just going to say close to 0. There's probably going to be some heat, a little bit of heat generated here. And so here, and so, even though the delta U is a state function, even though the energy is exactly the same, the amount of heat and the amount of work we do varies depending on how that was carried out. And so this is what we call a path-dependent function, because you aren't going to get the same amount of heat or work, for this delta U. The same thing goes for battery. A battery has a fixed amount of energy. It's a state function. You have a fully charged battery and you have a discharged battery. The delta U, the internal energy change of the battery, is always the same. But how you use the battery, if you use the battery to power a fan, you get some work done. But if you use the battery to power a little electric heater, then you aren't getting much work done. And so the same thing, you could use a battery to generate heat, or you could use a battery to generate work. Or mostly work or mostly heat, something like that. Yeah, because motors, there's going to be some heat generated from the operation of the motor, so it's hard to convert it into 100% work. And so this is why I put the 0 in quotation marks, because there's going to be some heat generated here. Not much, but we want to minimize that heat. Now, how does this apply to chemical reactions? Well, if we look at methane combustion, so CH4 gas plus CO2 gas at 25, going to CO2 gas plus 2H2O liquids at 25. The delta U here is always the same. Delta U is fixed. And so if I take a mole of methane plus 2 moles of O2 gas, I'm always going to get the same amount of total energy. But I can get different amounts of heat and different amounts of work. And so you see this reaction being used to do different things. For example, have you seen those methane, CNG? You heard of that? Compressed natural gas vehicles driving around, like buses and stuff like that. They're burning methane. And when they burn methane, do they want to maximize the heat, or do they want to maximize the work? They want to maximize the work, They want to drive the pistons of the engine, and create mechanical work. Obviously, they're going to get some heat too, but they want to minimize the amount of heat and maximize the amount of work. Whereas if you're using this to heat up a pot of tea, if you use this to heat up a pot of tea, do you want to maximize the heat or you want to maximize the work? You want to maximize the heat. And so, even though the internal energy here is always the same, the amount of heat and the amount of work we do varies depending on, how we burn it. All right, so that's out at the basic level. But now let's just look at the work. When we're doing work, we're just going to focus on one type of work right now in this chapter. And what type of work do we focus on here? We focus on the natural work of a chemical reaction, which is what kind of work? Yeah, volume changes. The thing about volume changes is, can you avoid volume changes? Yes, you can. You can avoid volume changes if you do it under constant volume conditions. If you do this in a bomb, do this reaction in a bomb, there's no volume change. But if you did this reaction at constant pressure, is there a volume change? Yeah, a constant pressure, there's going to be a volume change. Can you avoid the volume change? No. And so it depends on how you do this reaction. If we did this reaction in a bomb, then all the internal energy change gets converted into heat because no work can be done. There's no volume change. And so in a bomb, we do that. But if we did this at constant pressure, then there's a volume change. And if there's a volume change, then work was done. If work was done, then are we going to get as much heat if work is done? Well, it depends, because it depends on who does the work. And so depending on who does the work, it's odd. We'll get more heat or less heat. In other words, we don't. So when we burn a mole of methane, we don't always get the same amount of heat. It's obvious if you do, if you do this in a CNG vehicle, but even just burning it in the lab, and that's what we're going to focus on because we're only going to look at one work. And so from now on, we'll just consider PV work only. Then there are two scenarios here. One is constant volume. At constant volume, then this is pretty easy because delta U is equal to Q plus W. Well, what is W equal to? W is equal to minus P external times delta V of the system. Well, delta V of the system is 0, and so delta U is equal to Q. And so what we say here is delta U is equal to Q sub V, to keep track of it. V just means constant volume. Delta U is equal to Q sub V. Under constant pressure conditions, then there is a change in volume. And what is the change in volume? Well, here, we're going from about how many liters? This is 3 moles of gas. 3 moles of gas is about how many liters? 75 liters to 1 mole of gas, which is about 25 liters. And so we're going from about 75 liters to about 25, so we're losing about 50 liters of volume. If all of a sudden 50 liters of volume is lost, that's like, suction, vacuum. And what's going to happen? Well, the surroundings are going to just crush the system, right? Like that can. You just lost some milliliters in that can. And so here, in this case, well, delta U is always the same, so it's the exact same delta U, the exact same drop here in terms of energy, which is going to equal Q plus W. Now, we know what W is minus P external delta V of the system. Well, delta V of the system is going to be negative. Negative. So negative times a negative gives us a positive. And now, is heat being released or is heat being consumed? Well, heat's being released, so this is negative. And so the end result here is, this. The heat at constant pressure and the heat at constant volume are not the same. Okay, so this is going to equal QP, and plus dot dot dot. In other words, QP is equal to delta U minus W. But in this case, it's not a minus. We're not subtracting out the work. We're adding the work. Oh, actually, no. What is this going to be? This is going to be positive. No, we're going to subtracting out the work. Yeah. And so what's going to happen here is QP compared to QV, which one gives off more heat? If you were to heat a pot of tea, which would give you more heat? Doing it under constant pressure or doing it under constant volume? Constant volume? It looks like that because here, Q is equal to delta U, but these signs are always very tricky. And so let's do a quick calculation about that. So let's calculate this. Great, yeah. At least let's figure out what work is. All right, calculating the work, let me erase this one here. We need to figure out what V initial is and what V final is. V initial is we have 3 moles of gas, and it's 24.45 liters per mole gas. And so what does that give us? This is at 1 atmosphere. Wait. 73.35. V final is 24.45 liters plus, we have 2 moles of liquid water. So 2 moles of H2O liquid times 18.02 grams per mole times a milliliter is equal to 1.00 grams. And we need to convert that to liters. So let's go with liters. A liter is 1,000 milliliters. That works out. So liters and liters. And so this is going to be 24.45 liters plus 0.03604 liters, which is going to give us 24.486 liters. Okay, let's go ahead and calculate delta V. So delta V is equal to V final minus V initial. The V final is 24.486 minus 73.35. This is going to give us minus what? Does someone have it? Negative 48.864 liters. All right, the work is equal to minus P external delta V. And so delta V of the system. And so this is going to be minus, and this is 1 atmosphere. You know, I'm just going to call it exactly 1 atmosphere because it's a normal pressure. Times a negative 48.864. But this is going to be in liters atmospheres. So I want to convert this into joules. Converting into joules, it's 101.325 joules per liter atmosphere. Or 101.3. And so what do we get here? What do you get? How many joules?
Is that a 370?
Which one? This one? 325. 101.3. Just do 101.3. We just needed
4950.7.
4950.7 joules.
Yeah.
All right, this is what we call 4.9. How many sig figs are we allowed? 4. So 4.950 sub 7 kilojoules. Kilojoules, we usually write kilojoules because when we look at delta U's, delta U's are on the order of kilojoules. And so kilojoules will be our standard unit of this. And so about 4.9 or 5 kilojoules. All right, now when we compare the two, okay, I don't have the number, but we have to use some thinking here to figure it out. We see that QV, the heat under constant volume, is equal to delta U. Delta U is negative or positive for this. It's an exothermic reaction. Delta U, negative or positive? It's negative. And it's going to be negative on the order of thousands of kilojoules. So it's going to be negative some thousands of kilojoules of heat are going to be released in this. Whereas QP is going to be the same delta U, except now we have to do minus W. Well, we just calculated minus W. Minus W is 4.95. And so this is very tricky because when you think about subtracting out the work, we always think if you subtract out the work, we're going to have less energy, right? But in this case, when we subtract out the work, take a look. This delta U is negative. This term is going to be, well, it's minus a positive, so this term is going to be negative. A negative plus a negative is going to give you negative. And so which one gives off more heat? This is why I say let's do the calculation to confirm, because people said constant volume gives off more heat. Well, that's wrong. Constant volume does not give off more heat. Constant pressure gives off more heat because of all these signs are very tricky to track. And so when you track the signs, then you go, okay, negative and a negative, well, this is going to give me more heat. And so, well, how can it give more heat than the total energy change? If I look at the total energy, delta U is the total energy change. And so how can I get more energy than the total energy change? Is that even possible? Because that's the maximum. Let's say the maximum speed of this is 60 miles an hour, but how can you go 65 miles an hour? Is that possible? Well, that's possible maybe if you're going down a hill, right? If you're going down a hill, then, well, the maximum might be 60, that it can go by itself, but it's getting a little push from the surroundings, and the surroundings are hilly, let's say. Sometimes the surroundings are going to hurt you, like when you're going uphill. Let's say the car can only go 60, but you're going up a hill and it's going 55, 50, 45, because it's not that much. But then you go down the other side, down the hill, it's going to go more. And so where is this extra energy coming from? The extra energy is not coming from the methane and oxygen. Do you know where the extra energy is coming from? The extra energy is coming from the surroundings. The surroundings is giving this to the system. In other words, the surroundings crushing the volume, giving energy to the system. So the surroundings lost energy in doing that work. The system gained energy because energy is neither created nor destroyed, right? And so that extra energy is going to come off as heat for the system. So if you burn methane at constant volume, you'll get delta U. If you burn methane at constant pressure, you're going to get delta U plus a little bit of energy from the surroundings, which means more heat. And so burning this in the open lab is going to yield more heat than burning it in a bomb. Now we're going to look at all the scenarios here, which Actually, let's not almost a minute out. Yeah. How can we always, how can we predict how much heat we're going to get? Well, it's difficult to predict how much heat you're going to get because, did you do it in a bomb or did you do it in a lab? If you did it in the lab, what is the external pressure for that day? Because the external pressure is going to change. So, for example, if it's a high pressure day, then you would actually get more heat or less heat. This is only for this reaction. Thermo, we have to consider all scenarios. But in this particular reaction, if it's a high pressure day, would you get more heat or less heat than a low pressure day? A low pressure day, maybe a storm's coming through. You have a low pressure day. On a high pressure day, are you going to get more heat or less heat than a low pressure day? More heat. Surroundings are going to do more work. On a low pressure day, you're going to get, so, the heat's varying. The heat's varying all the time. But, heat is so important for us because we want to heat a pot of water and we want to predict how much heat is going into that pot of water. And so, what we're going to do is, how can we always get the same amount of heat? Is the question. So, how can we always get the same amount of heat? Like P external changes, Q, P. How can we get the same amount of heat? Q. Well, how can you get the same amount of heat consistently is you have to do the reaction exactly the same each time. And so if everybody does the reaction the same way you do it, then everybody else is going to get the same amount of heat you're going to get. Right? And so what we're going to do is this. In other words, when I ask how can we get the same amount of Q, I'm asking how can we make Q into a state function? And we can make Q into a state function by, like I said, doing it exactly the same way. So if you burn it exactly the same way each time, you'll get the same amount of heat. And so by combusting it the same way each time, and then you'll get the same amount of heat, basically. Well, how are we going to combust it the same? Well, that's not that difficult. You have to put some constraints. And so when we look at this, we know delta U is equal to Q plus W, and Q is equal to delta U minus the work. And so the total energy minus the work. It's tricky because the work is not always done by the system. In the last example, the work was done by the surroundings, which makes it very conceptually difficult to visualize. But anyway, we do this, and the first thing is we do this. We restrict this to constant pressure. Obviously, if this is constant volume, then the work drops out, so no problem with that. And we only have, well, this is a path-dependent function, what we call path-dependent. Then we do this. We restrict the work, to only P delta V work. And so we just do minus P delta V system. Now this is interesting because delta U is a state function. How about delta V? Is a change in volume a state function? Delta V, let's say we lost 50 liters. Does that only depend on the final and the initial volume? Is delta V a state function? Delta T is a state function. Well, the answer is delta V is a state function too. As is P. It's a state function. And so these are all state functions here. which means that now QP is a state function itself. Essentially, we're just doing it, burning it the same way each time. So with these restrictions, so we restrict constant pressure in P delta V work only. Then QP is equal to a state function. The state function we define as delta H. And so delta H is equal to delta U minus P external delta V. Or delta U plus P external delta V. So we get, or in other words, the work. This would be minus the work. Delta U minus 1. This state function is called the enthalpy change, delta H. So what is H itself? If we look at H, what exactly is H? And so if I'm looking at this, I got methane plus 2O2 gas going to CO2 gas plus 2H2O liquids. And then I have this delta H here. Well, delta H is the state function. Delta H is QP. So each time I burn this, I'm going to get the same amount of heat, which I call QP, which is delta H. QP is not necessarily a state function, but QP with these restrictions is. And so this is going to equal, delta U, right, minus the W. And which is delta U plus P external delta V of the system. Well, when I have H initial here, this is called the absolute enthalpy. What is the absolute enthalpy, and how does the absolute enthalpy compare to the absolute internal energy? Well, we know absolute internal energy. Absolute internal energy is the total energy, right? Well, what is absolute enthalpy? Well, absolute enthalpy is equal to the total energy plus P external V initial. And the final enthalpy, absolute enthalpy, is equal to the final internal energy plus P external V final. And so what is enthalpy? Well, enthalpy is the total energy, except we're factoring in the PV state. We factor in the PV state, so if we know what the PV state is initially and the PV state is finally, we can see how the system interacts with the surroundings. Right? If we look at internal energy alone, internal energy alone, we don't factor in the PV. The PV is energy as well, right? Pressure, volume, liters, atmosphere. But by factoring in this, we know the energy state here from the PV and the PV final. We can see how the system is going to interact with the surroundings in terms of P delta V work. And so the internal energy and the enthalpy are similar in the sense that they're both, the total energy, but this is the total energy factoring in the PV. And the change in total energy is going to be the heat. And so there's different ways to conceptualize this. Well, anyway, can I determine absolute enthalpies? Are absolute enthalpies determinable? No. Changes we can accurately predict. QP, just do a calorimetry experiment, you can get it, right? But internal energies are difficult. P external, V initial is easy. But the internal energies mean that absolute enthalpies are never determined. And so we never use this calculation, H final minus H initial. This is just not done. It's not done because we can't accurately determine the internal energy, absolute internal energy. And so you'll never do a H final minus H initial calculation. You're always going to get it some other way. All right, so let's go on to delta H. You know, when we look at delta H is equal to delta U minus W. And so sometimes it's very tricky because, you know, it's very tricky in terms of thinking, are you going to get more heat or less heat by doing it under certain types of conditions? And with the methane, we saw we're going to get more heat than the internal energy, right? And so this is the way to think about this. I like to use like a paycheck. You know, if you get a paycheck, what are you going to put in the bank? You're going to put in the net, right? And so delta H is the net, you know, what we're going to get. Delta U is what we'll call a gross, you know, but usually do you put in the, let's say you get paid $1,000. Are you going to put $1,000 in the bank? No, because you know, the government needs their tax, right? And so we have a tax here, but you know, sometimes we don't have any tax. You know, we'll just get the full gross amount, and sometimes we get a bonus, and so we can actually get more. And so what W is, it's going to be a tax, bonus, or you know, nothing, zero. There's no tax or bonus. So in the last example, with the combustion of methane, the work was a bonus. Because why was it a bonus? The surroundings did the work. If the surroundings does the work, you're going to get a bonus in energy. But you know, this is very tricky because you know, how you say this depends, you know. Are you looking at input of energy, or are you looking at output? Because this is going to be from the perspective of the surroundings. You know, the surroundings is the pot of tea. You're cooking the pot of tea, right? But it depends on what perspective you're looking at it, which is going to dictate things. And so this is why it's so hard to keep track of these things in your mind, because, you know, are you looking from the perspective of the surroundings, or are you looking from the perspective of the system? Or where's that energy going to? And so we'll look at some scenarios here. You know, under constant volume, then we don't have to worry about work, and it makes it easy. You know, under constant volume, then all the internal energy change is going to go into heat. But under constant pressure, then we got a number of scenarios. If we're looking at exothermic reactions, then we're looking at being the surroundings trying to benefit from all that energy, right? That's coming off the reaction. And so let's look at constant pressure exothermic first. And so U initials, actually, I'm not going to go U. Actually, should I go U? Okay, we're going to do it. We're going to go through all scenarios here. So first, let's look in terms of internal energy. U initial, U final. U initial, U final. Maybe I'll do the internal energies and then I'll do the enthalpies first. But here we're going to get delta U. Delta U is equal to what? So delta U is going to equal, well, we're doing this constant pressure and P delta V work. And so if we do that, then, you know, delta U is equal to QP plus W. In other words, QP here is going to be delta H. So this is going to be delta H plus W. Now, we're going to look. Delta H is not negative or positive? It's exothermic. Negative. Delta H is negative for exothermic processes. So our delta H term is negative. Now, let's say under constant pressure, V initial and V final, of the same thing. V initial equals V final, delta V is equal to 0. If delta V is equal to 0, then what do we see? How much work are we going to do? None. And so delta U is equal to delta H. And so under constant pressure conditions, if delta V and delta P are both simultaneously 0, then work is 0 and delta U. And so we just, this is what we call nothing. No tax, no bonus. We just deposit our full income. So if we get minus 1,000 joules, let's say delta U is minus 1,000 joules, then we're going to net all 1,000 joules. Does that make sense? And so in other words, this is equal to delta H. So let's say we minus 1,000 joules gross, minus 1,000 joules net. All right, let's say V initial is small, V final is big. Here. Let's say we have 1,000 joules here. And so delta U might equal minus 1,000 joules. We should get 1,000 joules of heat coming off this reaction. But are we? Well, let's see. Delta U is equal to QP plus W, which is going to equal delta H plus W. No, we're getting heat evolved from this. What is the work term? Well, if we look at delta V of the system, delta V is going to be positive or negative? Positive. V final is greater than V initial. I'm not going to write it down. But you can see the volume is growing. And so if delta V is greater than 0, that means delta V is positive. If delta V is positive, well, let's just take a look at delta H plus our minus P external delta V. Oops, did I just... So delta V of the system is positive, which means this term is going to be positive, which means this whole term will be negative, and which means we'll actually get this is tricky, which means this is going to be negative. And so, are we going to get more heat or less heat? More heat or less heat? Less heat. How can we get less heat? How can we get less heat? We should be getting more heat because, I mean, negative and this term is negative. Negative and negative is going to add up to negative, right? Aren't we going to get more heat? I mean, this was, the gross is equal to net. Gross is equal to net. This one, the gross, we look at that and we should get net even more, right? Well, in other words, this term is negative, this term is negative, right? The heat's negative, the work is negative, we should be grossing a lot more as the surroundings, correct? But we aren't. We aren't because delta U is a fixed. This is the same reaction. So delta U is minus 1,000 kilojoules. Delta U is a minus 1,000 kilojoules here too. And so both of these have to add up to minus 1,000 kilojoules. If both of these have to add up to minus 1,000 kilojoules, then this is what this means. This means we're going to get less heat. And so, thermo is drilled you know, all you have to do is you have to just drill these into your brain. How do you drill these? You drill these by going over it repeatedly. You know, repeatedly over and over. Because the people who just go through this once, they're totally lost. And so the way we drill this is this. We're going to label Q. Actually, let's label Q as red. We're going to label Q and then the W as green. And so when we look at this, delta U, this whole change here is going to be converted into heat because W is equal to 0. There's no work here, so the work term is 0, right? Now over here, I have 1,000 kilojoule. Let's say this is a 1,000 kilojoule drop. Well, delta U is the same here. It's the same reaction, but just done differently. This is a 1,000 kilojoule drop. But now, in this case, that 1,000 kilojoules has to be both the heat and the work. And so if I look at the 1,000, that has to be the sum total. Well, the heat's going to be this much, and let's say the work is this much. Usually work is less than the heat. And so here's my negative drop from the heat. Here's my negative drop from the work. Am I going to get more heat or less heat? Less heat. Do you see that? This is going to yield less heat. Why do you get less heat? Because the system had to do work. And so the way we say that is the system did work. The system loses energy doing work. If the system loses energy doing work, we're going to get less heat. Now here comes the scenario we just looked at with the methane. With the methane combustion, we went from a bigger volume, so V initials here, to a smaller volume, V final here. Delta U is the same, you know, let's say delta U is the same. It's always the same, it's a state function for a given reaction. But here, you know, when we look at this, delta U is equal to Q plus W. In other words, well, this is QP, which is delta H, right? And so, in other words, here, which one's bigger, delta U or delta H? Well, delta U is greater than delta H. Do you see that? Now we go over here. We do the same thing. You know, we have to keep all these relationships. You know, a lot of people, they can just see this visually in their mind and do that. But if you can't, then you write it out, right? You write out all the relationships and then try to sort of make sense of them. So, you know, we know this is QP. So QP is delta H under those conditions, plus W, and this is delta H plus a P minus P external, you know, delta B system. And so delta H, this is exothermic, so delta Q is negative, right? But take a look at this. Delta V of the system is less than 0. You know, we're shrinking in volume. If delta V of the system is negative, a negative times a negative gives us a positive. And so this term's positive. And so the heat on this is negative, but the work on this is positive. What does that mean? Well, visually, this is what it's going to mean. We're going to, oops, I'm not going to do that. Actually, let's do the work first. This means we have to do, who's doing the work? System or the surroundings? Surroundings. We'll look at the work first. The surroundings does work on the system. The system gains energy by the surroundings doing work on it. You see that? And that means the amount of heat that we're going to get is greater. And so here's where the work was a tax. Here's where the work is a bonus because we're going to net more heat from this particular reaction. And so in other words, you know, this is the same thing as saying, you know, QV is greater than QP, right? Over here we could say that, you know, delta U is less than delta H, or QV is less than QP. But it's a restricted QP. You know, it's not your QP. We have to realize that QP is a path-dependent function as well. You know, QP is not necessarily a state function until you put those restrictions on it. And so is that enough things to keep track of? Well, yeah, it seems like it, but you have more, right? You're going to have more stuff to keep track of. Because this is using internal energy diagrams. All right, next we're going to do the same three using enthalpy diagrams, enthalpy rather than internal energy. Here's where delta V is equal to 0 under constant pressure. Here's where delta V is greater than 0 under constant pressure. And here's where delta V is less than 0 under constant pressure. Okay, now when we switch to enthalpy diagrams, which is basically the same thing as energy, except we're keeping track of the pressure volume state initial and pressure volume state final. And so here's H initial, here's H final. Right? And here we're going to have delta H. Delta H, as long as we're under constant pressure and PV work only, is a state function. So delta H for all three of these well, we'll see what delta H is. Normally, delta H is equal to, you keep track of all this, delta U minus W, right? Internal energy change minus work. Now, here's where it's a little easier to see in terms of bonus or whatever. And so here, delta H is equal to delta U minus W. What's the work involved here? Work is 0. How come the work is 0? Constant volume. Okay, over here, delta H is equal to delta U plus minus W. What's the work here? Well, let's say delta U is a minus 1,000, you know, this is minus 1,000, so here we're going to net. And so this is our net, remember? And our delta U is our gross. And so here, we gross 1,000, we net 1,000. Over here, who did the work? System or surroundings? System did the work. If the system does the work, is that a tax or is that a bonus on the system? It's a tax. And so if the system does the work, then this is what we see here. You know, this work term, this is going to equal delta U minus a minus P external delta V, and I'm just going to call it. Delta V of the system is positive. If delta V of the system is positive, then the negative times the negative gives us a positive. And so what's going to happen is this is going to be, this might be, let's say if this might be a minus 1,000 joules, this is going to be plus 5 joules or plus kilojoules, you know, whatever. And so this whole term comes out positive. So in other words, this is a positive term, this is a negative term. That means we're not going to net as much heat. This is going to be a tax. Over here, delta H is equal to delta U minus W. Delta V of the system is going to be less than 0. So delta V is less than 0. This is negative. Negative times a negative gives us a positive. And so we're going to get this, which is negative, minus, or plus a negative, which means we're going to have a little bonus in energy here. because this is going to be negative. And so this is negative. A negative and negative means we're going to get even more heat released to the surroundings. All right, let's go through some more scenarios here. This is going to be internal energy again. But we're going to go endothermic now. So we have this one, B initial is going to be down here, B final is going to be up here. So B final and B initial, let's say the volumes are the same, delta V is equal to 0. And so here is our delta U. Our delta U is going to be positive now because it's endothermic. We're going up in energy here. So it's positive, and this is going to equal Q plus W. This means we have to input heat. Right? We input heat. And so how much heat do we input here? Well, if it costs you 1,000, you're going to have to pay 1,000, right? Because the work is 0. And so in this case here, well, this is QP. QP under certain restrictions is the same thing as delta H. So in this case, delta U and delta H are the same. The total internal energy change is the same as the enthalpy change because there's no surroundings involved here as far as the work goes. Okay, here delta U is again equal to Q plus W. This is Q under constant pressure conditions. Now, who did the work here? Well, did the system do the work or the surroundings? The surroundings did the work, right? And so since the surroundings did the work, then, well, what do we call that? Call it a bonus. But let's take a look. How does bonus work? And so delta V here is less than 0. This is reversed here. V initial, this is going to be V final up here. So V initial to V final. If delta V is less than 0, well, we know that this is QP plus a minus P delta V. I'm going to quit writing that to save time. Delta V is less, so this is negative. A negative times a negative gives us a positive. A positive plus a positive means this. Okay, so here is QP. QP and delta U are the same thing. Now here are these because the work is going to be positive here. And so both the heat and the work are positive. And so that means that the surroundings does some work on the system. The system gains energy. And then we have to input the heat. Do we have to input more heat or less heat than this one? To get this reaction to go, do we have to input more heat or less heat? We input less heat. That's how the bonus works in this case. It doesn't cost as much, or we get a discount. And so rather than saying bonus, I should say discount on this. We got a discount because where did the discount come from? The surroundings. The surroundings discounted the cost for us. Over here, we got the same delta U. Delta U is QP plus W here. QP is positive. But here, in this case, delta V is going to be greater than 0. If delta V is greater than 0, then delta V is positive. A positive times a negative is negative. And so this term is going to be negative. See that? And so, who did the work in this case? Who does the work in this case? The system does the work. And so the system loses energy doing work. System loses energy, how much heat do you have to input to make this go? Extra heat. You got to input extra heat because you got to cover the energy lost by doing the work as well. And so here there was a little tax on it. So you end up spending more. Does that make sense? Maybe, maybe not. But, you know, it can make sense. A lot of people just give up on this. They say it's too hard, but, you know, all it is just all it is just memorization, you know, and just repetition. It's easy. It's easy once you go through it enough times. It's not difficult. So don't put up any artificial mental blocks. All right, let's look at these scenarios in terms of enthalpy diagrams. Switch to enthalpy. H here. Okay, endothermic again. Here V initial is the same as V final. Delta V is equal to 0. Now we're looking at delta H. Delta H is equal to delta U minus W. Delta U is the gross, W is either the tax bonus or nothing. In this case, what is W? Zero. And so W is 0, that means this whole change is delta U. We'll have delta U as, how should I do delta U in blue. Work is 0. So here we have delta H is equal to delta U. And so our gross was 1,000. Our net's going to be 1,000. We have to pay 1,000 for this. In this particular scenario here, where V initial is bigger, V final is smaller, so delta V is less than 0. The volume is shrinking. And so here's our delta H here. Delta H state function. This is going to equal delta U minus W. Here, delta U is positive. What is W in this case? Shoot, I'm not going to finish today either. Well, W is going to be let's see this whole term. So this is negative, negative times negative is a positive, right? And so this whole term turns out to be positive. Is that correct? And so how should we read this? Well, the way we could read this is that delta U is the total energy, and so we have to pay even more than the total energy. Why do we have to pay, or do we have to pay more? No. Delta H. This is going to be delta U, and then the work term is going to be, actually, what is the work term going to be? The work term should be positive, right? Negative times a negative gives us a positive. So this whole term is positive. So this is positive, this is positive, then we should end up with something like this. The work and the delta U here. Let's make sure this makes sense now. So in this case, we ended up with the net we ended up with a bonus because the surroundings should have done the work. And so here we're going to end up getting more energy than the internal energy, but in all it's going to end up costing us more. But actually, let's compare it with this next scenario and just make sure that scenario is correct. Because this is the case where V initial goes to a bigger V final. Here. And see what happens here. And so here we have our delta H, again, which is going to equal delta U minus W. Delta V is going to be greater than 0. So in this case, the system will have to do work here. And so maybe I should write this out. Delta U minus P external delta V. If delta V is greater than 0, then that means if delta V is greater than 0, delta V is positive times a negative times a negative here. And so, in other words, this is positive, and then this whole term will be positive. So I made a mistake here because this is delta U, which is positive, minus P external delta V. And so the delta V here is negative. So if that's negative, this is negative times a negative, which gives me a positive times a negative, which will give me a negative. And so the work term should have been negative here. We're always adding these energies. And so the negative sign is going to be here. And so if the work is actually a negative term, when we add it together, we add the delta U and the delta, then this is backwards. And so let me redo this one here. I should have written it out earlier. And so the system has to lose energy doing work, right? The system loses energy doing work, which means the amount of heat you have to input is greater. So, does this make sense? Let's see. That case was easy. This case is still, see, even I have it drilled, but it's so easy to get mixed up, isn't it? So easy to get mixed up. But anyway, when we look at this particular scenario, okay, delta U is positive. And so because work was done by the surroundings, this is the internal energy change here, we call delta U. Actually, I made it in blue over there. Let's make it in blue here, not the heat. And so this is our delta U. So this is the total internal energy change. It didn't cost us this. And so if the gross was $1,000, we ended up spending less than $1,000. How? Okay, this W is the heat. We ended up spending less than $1,000 because the surroundings gave us a little bonus. This is in terms of mentally diagram. Maybe it's easier to visualize in terms of internal energy, but you go through them both and then you'll see. So when we look at this whole term, the work, well, now the system has to do work here. And so the system has to do work, we call this. And so it's going to cost the system energy. System does work. And the work plus the delta U is equal to delta H. And so delta U is the gross. So let's say it cost us $1,000 joules, we end up spending more than 1,000 joules because of the work that the system had to do. And this is the net. This is how much we have to spend. So we end up spending over $1,000 for this change because of the extra work that we had to add to the $1,000 here. Okay, does that make sense? And so delta U's 1,000, delta U's 1,000, delta U's 1,000. Here. Just do that. And so delta U's, let's say $1,000, something like that. So then try to visualize it. Delta H is the net you have to spend for this reaction to happen. All right, does that make sense? Probably not. Maybe not. But you know how you can make it make sense? You just, you don't just read it. You have to write it. You write it over and over again. You write it down like 5 times, 50 times over again. You make it make sense. Well, what do we do our reactions under? Most reactions in the lab take place under constant pressure or constant volume conditions. Constant pressure conditions. So for us, delta H is much more useful. Delta H is what we're going to call the usable energy from the chemical reaction. We can use that energy to do things with. And so, this is what we call the net energy. Even though the net energy, is QP, is it necessarily heat? No, the QP is just because we restricted the work, but what we could do is we can convert that net energy into work. So let me do one example problem doing that. The most common type of calculations you're going to have are heats of reaction, delta H type reaction. Actually, why did I get so far behind? Let me see. Well, let's do something like number 19 here as this is an example of delta H and delta U. Let's see how you understand it. Let's look at this reaction. This reaction goes to H2O gas. We don't know what the temperature is 2,500 degrees C. 2,500 degrees C. And so that's why H2O is going to be in the gaseous state. To produce very high temperatures. Do we want the hydrogen and oxygen to be at 2,500 degrees C? Well, in this case, let's look at this. Looking at this, who does the work? So this will be number 19. We're going to do this a little differently. Number 19, we start off at hydrogen and oxygen. It's going to be at higher energy. It's 1/2 O2 gas. Combustion of 1 mole of hydrogen form 1 mole of H2O gas. This is going to be at elevated temperature. And so, looking at this in terms of an internal energy diagram, what kind of scenario do we have? Well, what we have here is we have a bigger initial volume to a smaller final volume. And so if we look in terms of internal energy, U is going up here, then we got a delta U for this. Delta U is going to equal Q plus W. We're doing this under constant pressure conditions, so QP. Now who does the work for this? The system or the surroundings. This is going to equal delta H plus W. Well, it looks like the surroundings are going to have to do the work because we're shrinking down volume. If the surroundings does the work, then the system gains energy by having work done on it by the surroundings. And so what we can say here is that in terms of this, work by the surroundings increases the energy of the system, which means the heat we get out of this Q is going to be greater than delta U. This is delta H. And so in this case, delta H is greater than delta U. We get more energy than the total energy change because of the work done by the surroundings. This is internal energy. In an enthalpy diagram, maybe it's a little more tricky. With an enthalpy diagram, or maybe not, how do we do this? Well, now we're going to have delta H here. Delta H. Now delta H is going to equal delta U minus W. W, well, the surroundings did the work, so the system gains energy. So this term is positive here. This term is negative. And so what that means is, well, the surroundings is going to, well, the system is going to, what? How do you want to read this? Well, the way I usually read this is, okay, if this is positive, then this whole term's negative, and so we add the two. And so if this term's negative, then that means the system loses energy doing work. The system loses energy, or no, this has to be the same, because it has to be the same because we're going from V initial to V final. If we're going from V initial to V final, then the system gains energy, right? The system's going to gain energy by having work done. And so this is why the work is positive here. But when we look at this, well, we have a delta U, and we're going to minus W. And so in other words, the system gains energy by doing work. And what does that mean? Well, the system gains energy by doing the work, but in terms of delta H, these signs are all messed up. And so this is why I do this. We see the system gains energy, that's correct, but this whole term comes out negative. And what I like to think is, I like to think in terms of this plus this rather than this minus this, because when you start subtracting out energies, things get confusing, right? And so you always add the energies because the energies are always, and so when we add the energies, then this whole term comes out negative. And so you're absolutely right, the system, well, I don't know if you're thinking this way, but the system does gain energy doing work. But when it gains energy, we have to flip the sign because of the equation. And so even though this doesn't make sense, maybe, well, the work term is going to be overall negative because we add the two terms together. And so that means the work goes like this, and then Q delta U, excuse me, is going to be like this. This will be our delta U. All right, so in other words, the system gains energy by having the surroundings do work on it. Then we flip the sign. And so another way of thinking about it is we just add these two terms. This term gets its sign flipped, so the work gets inverted like this. And so in other words, we net more heat than delta U. We net more energy, and so this is where the work is a bonus, right? Not a tax. So you got it? I spent a lot of time, extra time on this. Spending extra time on chapter 7 because chapter 7 is the one that